Here at Kennedy Space Center. Frequently, our speakers at this time are those people we think of as the kind of the top echelon there, those astronauts. But the space program would not exist without hundreds and actually thousands of people working at dozens of sites all over the country and literally around the world. And with our upcoming launch of a very special new piece of equipment, we've been referring to it as a Mars rover, but it is so far sophisticated beyond what we've done in the past that we really need to use the term Mars Science Laboratory. Our speaker today comes to us from Boulder, Colorado. He is the principal investigator on one particular area of the equipment on board this Mars Science Laboratory. And without further comment, I want to present to you Dr. Donald Haskell.
Thank you very much. Can everyone hear me? Yes. All right, very good. So, welcome. You guys are here, I think, for a very, very good, very exciting week because I don't know if you're here on Saturday, but on Saturday we're launching the Mars Science Laboratory, which is NASA's next rover mission to Mars. And if you're anywhere on the coast or in the area, it's going to launch it. We hope it'll launch at 10 o'clock in the morning, 10 on Saturday morning. So that's why I'm here. The whole science team for the Mars Science Laboratory is here, and we're getting ready for the launch. And one of the instruments on the Mars Science Laboratory is dedicated in particular towards planning for future human exploration. In my opinion, I think the space program and exploration is one of the most exciting things that this country has done and a legacy for human beings in general. And so when we walked on the moon in 1969, that was an amazing achievement for mankind. And to send humans to Mars, I think, will be the next step in that level of achievement. So I'm going to talk today about one of the things that we need to do if we're going to plan to ever send humans to Mars, which is to measure the radiation environment on the surface of Mars, but also on the way to Mars, because radiation is an important element in exploring space. So what is radiation? Well, radiation is everywhere. You think of radiation when you get an X-ray, or you think of radiation when you get sunburn. There's a whole spectrum of radiation. It goes from radio waves, we listen to the radio, or the microwaves all the way down to getting sunburn and getting X-rays. And then space radiation, which I'll talk about next, is the higher energy radiation that you get when you actually get outside the Earth's atmosphere or in space. But there's actually radiation from other sources. We have radiation in the ground. There's actually radiation in food. Potassium has a few atoms that are radioactive. So even, for example, foods that have a lot of potassium, such as bananas, have very small amounts of radiation in them. So I think if you eat 600 bananas, that's the equivalent of one X-ray. Not to discourage you from eating bananas, they're very good for you. We live in a world of radiation, and some of it's good for you, and some of it's not so good for you. So, what is space radiation? Space radiation is, well, it's one of the top 5 challenges or problems that we have to solve if we want to go do deep space exploration. If we want to go beyond the moon and to the asteroids and to Mars, we need to understand the effects of space radiation and how to mitigate it, how to prevent it from hurting our astronauts. So there's really 2 types of space radiation. There's radiation which are called galactic cosmic rays. They come from outside the galaxy. And then, oops, hit the wrong button. All right, already doing it. And then there's radiation coming from the sun called solar energetic particles. So I'll talk about 2 types of radiation. And what does it do? Well, these are very high energy radiation, and it penetrates deep inside your body, and it can affect our cells or our DNA. So these are some images of DNA with a certain type of particle radiation going through it. So an X-ray would go through and does a little bit of damage to one little part of it, not very much. But if you got a heavy ion, as they call it, a really high energy or a really heavy particle coming through can do a fair amount more damage. And so the amount of damage that happens and whether you can repair or recover from it depends upon the type of radiation it is. It depends on the energy, and it depends on the actual particle type that it is. If you get just a small hit to one of your strands in your DNA, it can recover and everything's fine. You get a major damage from a very heavy particle, it can actually mutate it, the cell dies, and that causes cancer. So cancer is actually one of the biggest risks of radiation. It's a long-term risk. So what happens is, we want to go to Mars. It's typically a 2-year journey. It takes about 9 or 10 months to get to Mars. Then you have to stay on the surface of Mars for about 6 months to do your exploration, to do what you want to do on the surface. But you also have to spend 6 months waiting for the orientation of Mars with respect to the Earth to come back around so that you can come back to Earth. So you wait 6 months on Mars, and that takes another 9 or 10 months to come back to Earth. So the round trip to Mars, the shortest round trip to Mars is 2 years. So we have to plan for about a 2-year trip in terms of protecting the astronauts, keeping them safe, keeping them healthy. So why is radiation an important problem for going to Mars? There's two things that are fundamentally different between, well, there's lots of things that are different between the Earth and Mars. But from a point of view of radiation, there's two things that are fundamentally different. The Earth has a magnetic field around it. It protects us. It's basically a bubble which protects us from charged particle radiation. And it actually is what allows life to evolve here and for us to have this really fortunate planet to live on. And the other is that the atmosphere on Mars is much thinner than that of the Earth. It's only about 1% of the thickness of the atmosphere of Earth. So the magnetic field bounces charged particle radiation away from the Earth, and the thick atmosphere of Earth also protects us from deep space radiation. Mars has neither of those things, so we have to mitigate against it. We have to deal with it. We have to shield against it. So this is the rover that we're going to launch on Saturday. It's called the Mars Science Laboratory, but it's actually, the name is now Curiosity. We had a naming contest, and 10-year-old girl, 9-year-old girl picked the name Curiosity. She's getting VIP treatment here this week. She's got a tour coming up later on today. Maybe she's actually in the room, I don't know. But anyway, the new name of this next NASA rover is called Curiosity. It's about the size of a car. It's actually, here's a picture of a couple of the different NASA rovers. This is Curiosity on the steps out at the Jet Propulsion Laboratory in Los Angeles. These are the rovers that are on Mars right now, called MERV, or the Mars Exploration Rovers, and they're called Spirit and Opportunity. You may have heard about them. They're the ones that you see images of the surface of Mars from most recently. And they're small. They're kind of like the size of maybe a Tonka toy. And Curiosity is actually the size of a Cooper Mini, of a small car. So it's actually a very big rover. It's got 10 instruments on it. Here's a comparison between the two. So Curiosity is about 2,000 pounds, whereas the Spirit and Curiosity were only 165. And it has 10 more instruments, which weigh about 385 pounds. So that's a lot of instruments. We're going to do a lot of science with this rover. It's supposed to last at least 2 years, but really we think it can go 10 or more. So the launch window starts Saturday. If you're around on Saturday, please don't sleep in, because at 10 o'clock there's going to be a great launch to watch. It's launching on an Atlas V rocket, which is one of our biggest rockets that we have these days. And I think it'll take 9 months to get to Mars. So next August, sometime middle of August next year, we'll be landing on the surface of Mars. And it'll, as I mentioned before, its primary science mission is about 2 years, but it has the capability to last 10 years. And I'll mention in a minute why that's important for what we're trying to do here. So the science payload, I mentioned there's 10 instruments on board. There's cameras, of course, so we're going to get some really good images. We're actually going to get some good movies. Jim Cameron, who I believe he's the producer of Avatar. He's a co-investigator on one of the cameras here. So we expect that we'll get some 3D movies of Mars in the next couple of years. So here's a picture of the rover at the Jet Propulsion Laboratory out in Los Angeles. And you can get an idea of the size. These are people working in the clean room with the rover. It's a really big rover. In fact, this is one of the wheels of the rover right here, the sample wheel. So that's about the size of it. That's a real life size of the wheels of the rover. And in fact, if you follow the tweets on Curiosity, a lot of people are asking if there's room for an extra person they'd like to ride. They'd like to get one. And it's big enough to go, but I don't think we have the atmosphere for it. And on the way to Mars, it rides in a spacecraft like this. This is the aeroshell, which will help it go through the atmosphere when it comes down and to land on the surface of Mars. And then this is all the avionics and the computers and the jets to keep it going in the right direction. When you look at Mars up in the sky, it's just a dot. And I think it's an amazing accomplishment that we can launch something here on Earth and send it to this dot far off in the sky, and that we can actually not only land it on that planet, but we can land it on an ellipse which is about 10 kilometers in diameter. So here's the landing site that we've chosen. Here's the previous landing sites of all the other missions. So the other two rovers, Spirit and Opportunity, have landed here on Mars. These are the polar caps. You can see ice on the surface of Mars. Mars is actually, in a lot of ways, very similar to Earth. It's about the same size. It's about the same gravity. It has an atmosphere. It has water. There's water at the north and the south poles. So there's a lot of reasons why we think that life may have or could have evolved on Mars, which is why it's a sister planet to Earth, and it's very important to us. So Curiosity is going to land here. Here's some images of that landing site. It's at a place called Gale Crater. It's basically an impact crater, a meteor crater on the surface. It looks like a normal crater, except it's got this big mound in the middle, this big hill. And so all this structure actually provides a lot of opportunity to explore the different sedimentary layers. If you drive out west and you see, and you're driving in New Mexico or in Colorado, and you see these layers in the side of the hill, these sedimentary layers, you can actually sample those and you can learn about history as you go deeper and deeper. You're sampling back through time. Well, the same kind of structure we expect to find at Gale Crater on Mars, and so this provides us an opportunity to look back in time and see what Mars was like millions of years ago. So this is the technical scientific objectives of the mission. It's in scientific language, so it's sometimes a little bit difficult to understand, but basically the purpose of this mission is to understand habitability. Habitability really means the ability to have life, the ability to sustain life. So Earth is a habitable planet because there's air, there's oxygen, there's an atmosphere, the temperature is the right temperature. We have organics which we can feed, or which can provide nutrients for plants. So we want to find out if there's signs of things that would allow life to ever have lived on Mars. And that would be looking for water. Well, we know there's water, carbon-based materials, but also the life-limiting factors such as the radiation environment. And so these are 4 technical objectives of the mission. The 4th one is to characterize the radiation environment. And that's important because it's a life-limiting factor. If there's too much radiation, life really can't live or can't survive. Too much radiation, as you know, can kill you. So we want to characterize that amount of radiation and understand it, so when we send astronauts in the future, we're ready for it. So this is a picture of my instrument. It's called RAD, or the Radiation Assessment Detector, and it's about the size of a coffee can. It weighs about 3 pounds, and it sits in the top deck of the rover. And this instrument is going to measure the radiation on the surface of Mars, but also to prepare for future humans, but also to do those science objectives that the other instruments are also related to, in terms of seeing, for example, how deep must microbes or critters be below the surface of Mars to have ever lived. You know, how deep do we have to drill if we ever wanted to find evidence of past life on Mars that is in a safe zone that wouldn't have been destroyed by the radiation? So here's the objectives of RAD, and again, it's it's in quite scientific language, but there's three of them that are related to exploration. One is we want to characterize the radiation environment. The second is we want to translate it into what it means for human beings. And then we want to use it to test our models. We have models for everything. We have a model for what the radiation environment is. We think we know what it might be, but we need to test that. And then we also want to compare it with our models for understanding the possibilities of life in the past. So let's go back to the different types of radiation. Galactic cosmic rays come from the universe. They're very high energy radiation. It comes from explosions in the galaxy from every direction, called supernova or supernova remnants. It's relatively constant, except that it varies with the solar cycle. The sunspot cycle or the solar cycle varies about every 11 years. So it means that the sun becomes more active, and then it quiets down, and then it becomes more active, and then quiets down again. And this happens on an 11-year cycle. It's called the solar cycle. Well, when it becomes more active, it pushes the sun's atmosphere out, and that reduces the level of radiation from cosmic rays. And so as the solar cycle becomes more intense, the flux of cosmic radiation becomes less. And then in the minimum, when there's less radiation, when the sun is less active, then the cosmic radiation gets stronger. But it varies on a long term. It varies on an 11-year solar cycle. So this is why we want to keep Curiosity operating for 10 or 11 years. We'd like to characterize it over the course of an entire solar cycle. Then there's other type of radiation called solar energetic particles, which I mentioned a while ago. Those come from solar storms or solar flares. You hear about these every now and then. They're on the news. These are the things that would actually knock out satellites. Sometimes people would lose their satellite TV because the satellite got knocked out from a solar particle event or something like this. Well, these storms, as we become more and more dependent upon satellites and satellite communication, and for every GPS and for every aspect of our life here and the technology on Earth, we need to understand the causes of these storms, but they also will affect the environment on Mars. And so these are periodic. They last on the space of a few hours, or maybe a few days. And we need to measure these as well. And so when the big questions about those types of events are, well, when they occur, what are they like? And how bad does it get when they happen? I mean, when there's a big storm coming, you want to know how bad it is. It's like a hurricane warning. If it's a level 1 hurricane, it's okay, it's a hurricane. It's kind of scary. If it's a level 4 hurricane, it's really scary, and you want to get out of there. So we kind of look at these solar storms in the same way. We want to characterize the big ones, and we need to be able to characterize them on the surface of Mars. And then what happens when this radiation comes into the atmosphere? What's really interesting is you take one particle of radiation at the top of the atmosphere, and when it starts to hit the atmosphere, it breaks up into thousands of other different types of radiation. So you can have one iron particle at the top of the atmosphere, and it could break into hundreds of protons and electrons and neutrons and other different types of particles. So from one particle at the top, you get this whole cascade or shower of particles, and each one of these affects life differently. And you get, so for one particle coming in, you get this whole, each color represents a different type of particle. You get that whole range of particles coming through the atmosphere. The other thing is that each particle affects astronauts differently. So even though most of the radiation coming from galactic cosmic rays, for example, are mostly protons or helium, protons or helium aren't the things that do the most damage to humans or to astronauts. It's really the other particles like carbon or neon or iron. And so you need to measure all these particle types, and that's really what RAD is going to do. It's going to measure all of these different particle types. There's one other complication, which is neutrons. You may not have heard about neutrons. Those are neutral particles, so they don't have charge. They aren't deflected by the atmosphere. They just come right through, and they go through most things. But when they hit water, when they land in water, they interact with protons, which are about the same mass as a neutron. So while our body's 97% water, So if we have a neutron hit our body, it interacts with the water in our body and it does a lot of damage. Well, these neutrons also interact with the atmosphere and the surface. So we need to measure the neutron levels also on Mars, because neutrons do a lot of damage. So there's two things we're doing. We want to plan for astronauts going to Mars. Well, I talked about this 9 or 10 month cruise, this 9 or 10 month trip from Earth to Mars. Well, this is what the Mars Science Laboratory spacecraft looks like. This is actually what the next human crew vehicle is going to look like. And there's actually a big model of it out here in the foyer out here in the foreground. You can look at it, it's just the scale. So it's actually really big. But it looks very similar. It has a heat shield, here's a heat shield, and then it has the structure around it with, for humans it has windows. For our instrument going to Mars, we don't need windows, but they're shaped about the same. They have some of the similar elements, but we need to be able to figure out what the radiation will be like inside this vehicle. And so RAD will help us determine what that radiation will be like. So if you look at the crew exploration vehicle outside called Orion, and you see how big it is, you visualize that going to Mars. You want to measure what that's like going to Mars. Well, this is pretty big too. And this is still about 10 feet across, so that's not too far off, but it's very similar. And then we also want to predict what the radiation is on the surface. So this is kind of some plots that show these colors represent the amount of radiation on Mars. And so the thickness, I mentioned earlier that the thickness of the atmosphere affects how much radiation goes through. Well, these maps of Mars show that these regions don't have as thick of an atmosphere. It's like living in Colorado. They don't have as thick of an atmosphere, so they have a higher radiation level. We actually in Colorado have about twice the radiation dose that someone here in Florida gets, just because the thickness of the atmosphere, where it's a mile higher than sea level, we get more radiation in Colorado. So these regions are lower and they have less radiation. So we want to validate that. We want to verify that. And then here's this picture of RAD again. This is kind of the details which I mentioned before, but it's got all the guts to measure charged particles and neutral particles in something that's the size of a coffee can. It takes about 4 watts, which is about the amount of energy that your toaster takes, and it'll operate basically every hour for the entire mission. This is a cross section of the inside of it, and this is kind of the detail of what it looks like. The charged particles come through here, and they deposit energy into different detectors, marked A, B, and C. And we have 2 other types of scintillator detectors, which would flash when they get a particle ahead of radiation. They measure the neutral particles, and then all the electronics are down in the bottom of it. So we have 3 electronics ports, and the whole thing is really small, and it's completely autonomous. So this is how it sits in the rover. Here's where it sits. It sits in the upper left-hand corner. And here's this field of view looking up towards the sky, kind of in a cone, 65-degree wide cone. And so we're a passive instrument. We operate completely independently, and we're going to measure all these particle types. If you've taken chemistry or physics, you know protons have a charge of 1, and helium has a mass of 1, and helium has a mass of 2. You go all the way up to iron, which has a mass of 26, so it would be 26 times as big as a hydrogen or a proton. We're going to measure all these particles with a whole range of energies, and we're going to measure neutrons and other types of particles as well. And it's going to be operated very simply. We don't, in fact, the rover doesn't have to do any commanding for us, really. We basically take data, we store data, and then we put ourselves to sleep, and we wake ourselves up. And we do this on a 1-hour cadence, or a 1-hour basis. So every hour we take some data, maybe for half an hour, maybe for 15 minutes, and then we store the data and we put ourselves back to sleep. And we do this every hour so that we get a time series of data of the radiation on the surface of Mars, pretty much every hour. And here's a picture of RAD being installed in Curiosity. Here's RAD being held by the guys in the clean room. And this is going in from the bottom. So actually the rover is turned upside down. And we're sticking it in from the bottom. And here it is, right? This is actually a picture taken here at Kennedy Space Center just about 2 months ago, as the last thing we did before we took off a cover. It's called a remove before flight cover. All the things that you don't want to fly to Mars that you need to protect your equipment, you call it a red tag cover or a remove before flight cover. It's red, it's got a big thread on it, a big flag on it, so you can't miss it, so you don't want to forget taking it off. So now RAD is ready to go. It's on the rover, and that's pretty much it. That's what we're going to do. And on Saturday we're going to launch. We're going to go to Mars, and you can find out more about this on a couple of our different websites. I mentioned some of the tweeting going on. There's over Facebook pages. This is the website for the Mars Science Laboratory, but I think Mars Science Laboratory Curiosity is also on Facebook, and I think it has at least 150 tweeters are here in Cocoa Beach, ready for this. They're getting ready to do a tweet up to get everyone knowing what's going on. There's a video that shows the landing, which I don't have here, but you can go to this. Actually, you can probably find this video from this website. And then there's actually a video, which is also linked from this website, talking a little bit more about radiation and about RAD. You can also do a search on measuring radiation on Mars. But that's pretty much it. Keep your fingers crossed for Saturday, and thank you very much.
Now, ladies and gentlemen, if there are questions, let me bring the microphone to you so everyone can hear.
Let me mention, I have some RAD stickers if you'd like to get some. I think we have some up here up front. You can put them in the back. So if you'd like to get a RAD sticker to put on your whatever.
Doctor, how many people did it take to build RAD, and how long?
So we started building RAD in 2005. So we spent about 6 years now on RAD. We were originally scheduled to launch in 2009. So we actually delivered it. We were ready to deliver it in 4 years. So about 4 years, and it's probably the efforts of 40 or 50 people total. That's typical for each of these.
Thank you. Are you measuring radiation on the way to Mars, did you say as well?
Yes.
And how are you doing that? Through this as well?
Through the spacecraft. So it's actually, it's very interesting because it'll be simulating what an astronaut will see when an astronaut goes on space. So the charged particle radiation is shielded a little bit, but the neutrons are not shielded. And we'll see those. Actually, they're actually created by hitting the charged particles hitting the spacecraft. So it'll be a different environment than if it was another advanced spacecraft. It's representative of what a human environment is.
All right, and we have another question from one of the younger members of our audience.
Does radiation affect machines?
Yes, it does, actually. That's a really good question. It affects electronics because it can cause an electronic to your computer. If your computer gets hit with radiation, it can, what's called a single event upstake. It basically flash and will turn off. So yeah, it affects machines, primarily the electronics. Good question.
Are there other questions? Yes.
How will the radiation affect the Curiosity machine?
Well, so we have to shield our electronics, just like we do humans. And we have thick shielding around all of the electrons. And it also, the neutrons will actually cause the metals to fatigue over time. So it affects it. It's one of the things that we can study and we study. It'll make it older. Here's the word. Hey, Sarah.
Yes?
Here's the word.
Okay. Yeah. We've got a lot of takers up here down.
Okay, good. Well, here they are. Any other questions? Thank you very much.
Thank you.
Sorry?
Keep the batteries.
It'll last a while. The launch pad is the Atlas 5 launch pad. I think it's about LC-37 maybe. It's going to go east. Yes. It's going the same direction as the shuttle. Yeah, because we want to go over the ocean so that if something ever happens to it, it falls into the ocean. Same way. Exactly. Good. Thank you.